So today we are going to discuss heterogeneous graphs and knowledge graph embeddings. And in particular, we will be focusing on methods for knowledge graph completion. So the topic for today is about, first to talk about a concept called heterogeneous graphs. And basically, so far in our course, we have been handling graphs that have only one edge type and only one node type. We just said there is nodes and edges, and nodes are connected with edges. So now the question will be, how do we handle graphs, directed, undirected graphs that have multiple types of connections, multiple types of nodes, multiple types of links between them? And this is the notion of heterogeneous graphs. Heterogeneous in a sense that they contain heterogeneous sets of entities and heterogeneous set of edges. And what we are going to talk today about in the first part is to discuss about relational GCN that takes care about different edge types, different relation types. And then we are going to talk about more specifically about knowledge graphs, which are a class of heterogeneous graphs. How do we do knowledge graph embedding, and also how do we do a very common task which is called knowledge graph completion. So let's start with heterogeneous graphs and discuss relational GCN, so relational graph convolutional neural network. So a heterogeneous graph is defined by a quadruple. It's defined by a set of nodes, we'll call them V. Nodes could have different types. It is defined by a set of edges that connect different nodes, and each edge has a different relation type. So this means that edge is now a triple that says node I is connected to node J via relation R, and then also each node is of a different type, and I can get the type of the node by looking into this function or set T. So basically I have nodes and edges where every node is labeled by a type and every relation is labeled by a type. So what would be some examples of heterogeneous graphs? One very common example is in biomedical field, where you can basically take different biomedical entities and then relationships between them and represent this as a heterogeneous graph. So for example, in this case, I would have different node types, I would have diseases, I would have drugs, I would have proteins, I would have different edge types, which is different types of relations between these different types of entities. And then, an example of the node here could be the disease migraine. And then I also have different edge. For example, it would be that a particular drug treats a particular disease. And then, how can this, and then I can have different types of relations between them, like causes and so on and so forth. So that is one example of a heterogeneous graph with different types of entities and different types of relationships between them. You can also think of event graphs as another example of a heterogeneous graph, where again I could have different types of nodes, different types of entities, like for example a node type could be a flight. I could have different edge types, it would be a destination of a flight, and then I could have, the destinations are different airports like the SFO, and create different types of relationships between these different entities. This is another example of a heterogeneous graph. So now if we are given this type of graph where we have different types of nodes and different types of relations between them, then we would like to be able for our model to handle this heterogeneity, in some sense to take advantage of it, to learn that, treats a given drug treating a disease is a different type of relationship than a given protein interacting with another protein. So how are we going to do this is we are actually going to extend our GCN, so graph convolutional neural network, to be able to handle different types of relationships. And we will call this a relational GCN. And we will so far, right, we defined GCN on one type of a relation and one type of a node type, so on simple graphs, and now we would like to expand it to more complex heterogeneous graphs. The way I want to explain this is first remind you about a GCN, and then it will become very natural how do we extend it. So the first question when we think about a graph neural network is, how does a GCN operate, and how does it update a representation of a given target node in the graph? And we have discussed this through this notion of a message passing and computational graph, where for a given target node, let's say A, here is its corresponding computation graph, where every node gets information from its neighbors. Notice that perhaps from the previous classes we talked about undirected graphs. Here now the graph is directed, so every node only gathers information along the direction of the edges. So A gets information from B, C, and D, but for example node B, even though it has two edges adjacent to it, it only gathers information from C because C points to it and B points to A. So that's why, for example, here the graph structure, the computation graph structure is like this. So this is now how you can take into consideration relations of edges. Now that we have reminded ourselves of how to unfold a graph neural network over a directed graph, we then talked about what does define a single layer of a graph neural network. And we define this notion of a message, where every node computes the message coming from its children, and this message depends both on its message from the previous level as well as the neighbors that it has at the previous level. And then the way the aggregation of these messages happens is that the node V will basically take these transformed messages from each of the children and aggregate it in some way, combine it with its own message, and produce the message or the embedding of the node at the next level. And in order to add expressivity in terms of feature transformations, not in terms of capturing the graph structure, but in terms of capturing the feature transformations, we can then also add nonlinearities, activation functions like sigmoid, ReLU, and so on. This is how we think of graph neural networks. Now, going back to the GCN, in a single layer of GCN is defined with the following formula, right? It's basically a node goes over its neighbors U, takes the previous layer representations of the nodes, normalizes it by the parents in degree, sums them up, transforms them, and sends them through a nonlinearity. So what does this mean is that the way you can think of this is that the aggregation of a GCN is a average pooling type of operator because of a summation and normalization here, and then the message transformation is simple linear transformation. So now what happens if we have multiple relation types, right? What if I have a graph that has multiple types of relations? The way I will denote this is that I will use edges of different colors, and here I label them as R1, R2, R3, where basically says that A and B are connected according to the relation R1, while B and C are connected by relation R3. So that's the way we are going to think of the input graph now. And the way we can now generalize GCN to this kind of heterogeneous graph is to use different network transformations, different neural network weights, different neural network parameters for different relation types. So it means that when we are doing relation transformation, when we are doing message transformation, we are not going to apply the same matrix W for every incoming edge, but we are going to apply a different matrix W depending on whether what is the kind of the relation that we are considering. So if we have three different relation types, we are going to use three different types of W matrices, one for relation 1, one for relation 2, and one for relation 3. So now, if I look at how does the neural network computation graph for the node A look like, what is different now is that these message transformation operators, these W's, now have a color associated with them. So it means that the message coming from, let's say, node B and the message coming from node D towards node A will be transformed using the same operator, the same W, because the message is traveling along a relation type R1. While, for example, the message from node C that is connected to node A with relation R2 will be transformed with a different transformation operator, the red one. The red one is designed for R2. So here you see the difference, right? And for example, this means that now how we are going to write this up is that we have these transformation matrices W that are also indexed by the relation type, right? So in a relational GCN, the way we write out the message propagation and aggregation is the following. We basically say to compute the message of node V at level L+1, we are going to sum up over all the relation types. For every relation type, we are going to look at who are the neighbors of node V that are connected to node V according to this relation type R. Then we are going to take the transformation matrix specific to that relation R, to take the messages from the neighbors that are neighbors U that are connected to V according to this relation type R, and we are also going then to do the embedding of the node V from previous layer and transform it. The important difference here is that W's before they used to be only differ layer by layer. Now what happens here is that we have W for every layer for every relation. So another thing I did not explain is what is this C sub VR. This is simply a normalized node in degree compared to that relation. So it's basically the number of incoming relations of a given type R to the node V. This is still a graph neural network. It is still, I can write it out in this formalism of a message transformation and aggregation, where basically each neighbor of a given node V transforms its previous layer embedding according to the matrix W, but now W changes for every based on the type of the relation between U and V. And here we transform the message from node V from the previous layer to the embedding from the previous layer into the message for the previous layer, and then the aggregation is still simply a summation, right? We take these transformed messages based on the embeddings from the neighbors from previous layer where the transformation is relation specific, as well as node's own embedding from the previous layer transformed. We add all this together to get the embedding at the next layer. So this is called relational GCN. So basically a relational graph neural network or a relational graph convolutional neural network, where the main difference is that now we have different message transformation operators based on the type of the relationship between a pair of nodes. And this is denoted by this subscript R that denotes the relation type. So this is how we defined RGCN. The point is now, right, we said that for every relation R, we need capital L matrices, meaning these transformation matrices are different for every layer of the neural network, of the graph neural network, and they are different for every relation. So the problem then becomes, if you ask what is the size of this matrix, the size of the matrix W is simply the embedding dimension on the lower layer times the embedding dimension at the upper layer, right? So it's basically dl and dl+1 are the embedding dimension at layer L and the embedding dimension at layer L+1. And this can quickly be a few hundred, these D's are in the order of a few hundred, maybe up to a thousand. Right? So now the problem is that I have one such matrix per every layer, and I have one such matrix per every relation type. And because heterogeneous graphs, and in particular knowledge graphs, can have hundreds, can have thousands of different relation types, then you can get tens of thousands of these different matrices. And each matrix is dense and can have quite big size. And the problem then becomes that the number of parameters of this model, of this RGCN model, tends to explode because it grows with the number of different relation types. And there can be thousands of different relation types. And one problem is that the model becomes too big to train. And then the other problem is that the model has too many parameters and overfitting can quickly become an issue. So what I want to discuss next is two approaches how to reduce the number of parameters of this RGCN style model using two techniques. One technique will be to use block diagonal matrices, and the other one will be to use basis or dictionary learning, as it is called. So let me first talk about use of block diagonal matrices. So the key insight is that we want to make these W matrices, the transformation matrices, we want to make them sparse. And one way to make them sparse is to enforce to have this block diagonal structure. So basically, non-zero elements are only along the specific blocks of this bigger matrix W. If you think about this, this will now reduce the number of non-zero elements, the number of parameters in each W you have to estimate, because you only have to estimate the blocks, these two green blocks, and you can basically ignore or assume these empty parts of the matrix are zero. So if you assume, for example, that W is composed from B low-dimensional matrices, low-dimensional blocks, then the number of parameters is going to decrease by a factor B. So if you set B by 10, you have just reduced the number of free parameters that you need to learn or estimate by a factor of 10. Of course, what do you lose? What you lose is now that if you think about this as a transformation matrix, what you lose is that embedding dimensions that are far apart from each other, they cannot interact with each other, right? So this means that, for example, here only embedding dimensions 1 and 2 can interact with each other, but not, let's say, 2 and 3, because they are in different blocks. So it may require several layers of propagations and different structures of block diagonal matrices to be able for embedding dimension 3 to kind of talk to embedding dimension 2. So basically what this means is that only nearby neurons or neurons in the same block can talk to each other and exchange information with each other. So perhaps your GCN, GNN may need to be a bit deeper, but you have reduced the number of parameters significantly, which will lead to faster training, perhaps more robust model, less overfitting, and so on. So that's the technique of block diagonal matrices, where basically you reduce the dimensionality of each W by assuming a block diagonal structure. Second idea how to make this RGCN more scalable and its learning more tractable is to build on the key insight, which is we want to share weights across different relations. Right? We don't want to consider relations as independent from each other, but we want relations to kind of share weights to also share some information. And the way you can achieve this very elegantly is that you represent the weight matrix, the transformation matrix W for each relation as a linear combination of basis transformations or as of basis matrices. And you call these basis matrices as your dictionary. So this is also called dictionary learning. So let me now explain. The idea is that now your W, R, is simply a weighted summation over this dictionary of matrices V and I have capital B of them. right? So basically the idea is that I'll have a dictionary of matrices V, and then to come up with a transformation matrix for node W, then basically what I have to do is have these weight scores, importance weights A, that say how important is a given matrix V sub B for a given relation R, right? And the point is that these matrices V are shared across all relations. So I can think of matrices V as my basis matrices or as my dictionary. And then these weights A, those are importance weights for each matrix. So basically I say the transformation matrix for a given relation R is some kind of linear combination of these basis matrices, where these linear combination weights are learned for every relation. Right, so this means that now every relation only needs to learn these importance weights, which is just capital B number of scalars rather than a large number of different transformation matrices. So now basically every relation-specific transformation matrix is simply a linear combination from this dictionary of matrices V. And that's an elegant way how to reduce the number of parameters, because B can be relatively small, let's say, I don't know, 100 or a 10, but maybe you still have 1,000 different relation types. And you basically say, I will represent every of the 1,000 relations as a linear combination from my dictionary of 10 weight matrices. And that's a very elegant way how to reduce the number of parameters. So now that we have talked about this scalability issue of RGCN with two different approaches, one being the block diagonal structure of the transformation matrix W, the other one being that we cast learning of W as a dictionary learning problem, which basically means we assume there is an underlying set of, let's say, 10 different basis matrices, which we call dictionary, and then every relation-specific transformation matrix is simply a linear combination of the matrices coming from the dictionary, also reduces the number of parameters, makes the method more robust, and speeds it up. So now that we have RGCN, what we want to do is also talk briefly about how do you define various prediction tasks on the graph, on the heterogeneous graphs. So in terms of node classification or entity classification, it is all kind of as it used to be, right? So RGCN will compute a representation or an embedding for every node. Then based on that embedding, we can then create a prediction head. For example, if we want to classify nodes into k different classes, then in the final prediction head will simply be a linear transform that will basically take the embedding, multiply it with a weight vector, pass it through a non-linearity like a sigmoid, and we can interpret that as a probability of that given class. So basically we will have a k head output where we each and then have a softmax on top of it, so that basically we interpret that as a probability that that a given node is of the kth given type or kth head. That's how we think of node classification. For link prediction, things get a bit more tricky because now links have different types, and we don't want to simply split links randomly as we did it so far, because some types might be very common and other types might be very uncommon, right? Some relation types might be very common, some relation types might be very uncommon. So what we would like to do is, for every relation type, we would like to split it between training message edges, training supervision edges, validation edges, and test edges. And then we would like to do this for every of the relation types and then kind of merge all the message edges for the training, take all the training supervision edges for each separate relation type into the training supervision edges, and then same for validation edges and for test edges, right? So kind of the point is that we wanna independently split edges from each relation type and then merge it together, these splits. And the reason we want to do this is because this means that even for a very infrequent, very rare relation type, some of the instances of it will be in the training, some of instances will be in the validation, and some will be in the test set. Because the point would be, if we just blindly split the edges, just by chance it can happen that a very rare edge type does not appear in your validation set, because it's just too rare and by chance none of the edges landed there. So that's why we want to do this, what is called stratification, where we independently split edges of each relation type separately and then merge it all together. So we have these 4 different edge buckets: training message edges, training supervision edges, validation edges, and test edges. We do this splitting for each relation type separately and then merge it all together into the 4 sets, and then, you know, everything still applies as we talked about link prediction. So to tell more, give you more details about how you formalize link prediction in heterogeneous graphs, imagine, you know, I want to be able to predict whether there is an edge, or what's the probability of an edge between nodes E and A, and that edge is of type 3, of relation type 3. So imagine that this edge is a training supervision edge, right? And let's say that all other edges are training message edges. So the way I would now use the RGCN to score these edges, I would take the final layer embedding of node E, I would take the final layer embedding of node A, and then I would have a relation-specific scoring function f that would basically take these 2 embeddings and transform them into a real value. So one approach to do this would be to use this kind of bilinear form, where basically I take one embedding, I have the transformation matrix in between, and another embedding, so that at the end, basically this take the embedding of node E, transform it, and then dot product it with embedding of node A, and I can interpret this, perhaps send it through some sigmoid or something like that. I can interpret this simply as the probability that there is an edge of relation type, let's say R1, between nodes E and A. So that would be one way to actually formalize and instantiate this problem. Now, how exactly am I thinking about this during training? So let's assume again that this is the edge that is a supervision edge, and let's think that all other edges in the graph are the training message passing edges. So we want to use the training message passing edges to predict the likelihood or the existence of this training supervision edge of interest. What we also have to do in link prediction is that we have to create negative instances. We have to create negative edges. So the way we create negative edges is by perturbing the supervision edge. So for example, if this is the supervision edge, then one way how we can do it is that we corrupt the tail of it, right? So we maintain the head, we maintain node E, but we pick some other node that node E is not connected to with the relation of type R3. So in our case, we could, for example, create an edge from E to B or from E to D. So this could be our negative edges. What is important when you create negative edges? The negative edges should not belong to training message edges or training supervision edges. So for example, edge to the node C cannot be a negative edge because node E is already connected to the node C with relation type 3. So this is not a negative edge because the edge already exists and it's of the same type as here. So we don't want to create this contradiction. So we have to be a bit careful when sampling these negative edges. Now that we have created a negative edge by perturbing the tail so the endpoint of the supervision edge, we can now use the GNN model, the ArcGCN, to score the positive as well as the negative edges. And the loss function we would want to optimize is a standard cross entropy loss, where basically we want to maximize the score of the training supervision edge. We would like to maximize the scores of this guy, and we would like to minimize the score of negative edges, like for example E to B or E to D. So that's how we would write down the penalty as I show it here, and then use the optimizer, stochastic gradient descent, to optimize the parameters of ArcGCN to basically assign high probability, high score to the training supervision edges and low score to negative edges. Now that we have the model trained, now assume we move to the validation time. We want to validate the performance of our model. So let's assume now that the validation edge that I'm interested in is this edge between node E and node D, and I'm interested whether it's of type R3. Then in this case, training message edges and training supervision edges basically means, in my example, all existing edges of the graph are used for message propagation. And then at the validation time, I'm basically using all these solid edges to do the message propagation, and I'm trying to score the value of this particular edge from node E to node D. Right, and again, the intuition here is that the score of this edge should be higher than the score of, let's say, all other edges that are in some sense negative or that don't exist in the data set yet from node E. So for example, this would mean that the score of this node edge from E to D has to be higher than the one from E to B in our case. And I cannot consider these other edges because they are already used as message passing edges in my validation ArcGCN. So notice that it is important that these sets of edges are independent from each other when we score them. So how would I evaluate this? Right, I would use the ArcGCN to calculate the score of edge ED according to the relation type 3. I would then calculate the score of all the negative edges. So in my case, only two possible negative edges of type R3 are E to B and E to F, right? I cannot do A and C because they are already connected according to the relation 3, so that would be kind of a contradiction. So I have only two negative edges, and the goal then is basically to obtain a score for all these three edges. We rank them, and hopefully the rank, the output score of the edge ED will be higher than the output score of EF and BF. And then how do I usually evaluate calculation matrix? How do I usually evaluate? I can do either what is called hits, which would be how often was the correct positive edge ranked among top K of my predicted edges, or I can do a reciprocal rank, which is 1 over the rank of the positive edge ranked among all other negative edges. And then you can do mean reciprocal rank, and the higher the mean reciprocal rank, the better. The higher the hits score, the better. So let me summarize. We talked about relational GCN, which is a graph neural network for heterogeneous graphs. We talked about how to define it. We talked about how to have relation type specific transformation functions. We discussed about how to do entity classification as well as link prediction tasks. We also discussed how to make relational GCN more scalable through making matrices W block diagonal, or using it as a linear combination of basis transformations, so this kind of dictionary learning approach. And of course, you can take ArcGCN and extend it in any way you like, right? You could think that you could have RGen, you could have RGraphSage, you could have RGraph attention network. So all these basic fundamental GNN architectures that we already discussed, it's kind of natural to extend them to this multi-relational case by basically adding relation-specific transformations. So it's kind of natural that how you can play with this model and make it more expressive and richer and so on.